Module 5, Lesson 5 is Factors and Multiples. The content objective says students will solve problems by finding the greatest common factor and the least common multiple of two whole numbers. The pacing guide suggests this will be a 2-day lesson. Let's get started. Floral design is the art of taking plants, including flowers and other materials, to create a pleasing composition. It takes a keen eye and creativity. Did you know it also includes math? Samantha's older sister is getting married, and she is helping design the floral centerpiece for the dinner tables. They decided they want to make each centerpiece exactly the same with 2 different types of flowers. Samantha and her sister have 250 roses and 175 peonies. I guess that's what that is. Have no idea what a peony is. If they want to use all the flowers to make identical centerpieces, what is all the possible combinations of roses and peonies that could be used in each centerpiece? These are the kind of things we're going to be learning about in this lesson. Our inquiry question says, how can finding the greatest common factor help to solve real-world problems? Well, let's dig into it. Lucy is making balloon arrangements for decorations at her birthday party. She has 8 blue and 12 green balloons. What is the largest number of balloon arrangements she can make if she wants to use all the balloons in each arrangement is identical? And it says, drag balloons to the tables to see if you can make 2 identical arrangements for all the balloons. Well, I'm going to say I can put a blue and a blue. Probably need to have that blue a little higher there. Another blue and another blue. Another blue and another blue. Another blue and another blue. And that's all my blue balloons. And then for the green balloons, we're going to do, whoops, the green balloon didn't want to stay there. 1, 2, 3, 4. 1, 2, 3, 4. But we're not done. We still got balloons left. 1, 2, and 1, 2. And now you've got 2 different tables with the same numbers of each color of balloons. There's 4 blue balloons and there's 6 green balloons. But what if Lucy had 3 tables? Then what could she do? Well, that's going to be a little bit more challenging because 8 is not really divisible by 3. I can see that I could do the greens, 1, 2, 3, 4. 1, 2, 3, 4. Yeah, it's a little low. And 1, 2, 3, 4. So I've got the same number of greens on every table. What if I was going to the blues? 1, 1, and 1. 1, 1, and 1. And then I'd have 1, 1, and that last table over there is not going to get the 3rd balloon. So you're not going to be able to have the same number of blue balloons on every table. That makes it a challenge now, doesn't it? So why do you think you were able to divide the balloons into the 2 arrangements, but it didn't work to divide them into 3 arrangements? The answer, it comes down to this little thing called common factors. You were able to get greatest common factors of 4 balloons for the blue and 6 balloons for the green when you were dealing with 2 tables. But when you moved up to the 3 tables, you couldn't get a common factor for the blues for all 3 tables. There was no way you could divide 8 balloons and have them fit 3 tables without popping a balloon. Now the question asked, do you think Lucy could be able to do 4 tables? Well, is 8 a number that's divisible by 4? It is. So you could have 2 blue balloons on each table. How about 12? Are the 12 green balloons divisible by 4? Yes, they are. You could have 3 green balloons on each table. So it would be possible to do 4 tables with equal numbers of balloons on them. To test this prediction, all we have to do is start dragging balloons. I said it'd be 2 blue balloons on each table. And I said that it would be 3 green balloons on each table. 2, 3. 1, 2, 3. 1, 2, 3. And 1, 2, and 3. And now all the balloons have been used. We have common factors of 2 for the blue balloons and common factors of 3 for the green balloons. So did my prediction hold true? Absolutely it did. Do you think we could divide it into 5 identical arrangements? No, we couldn't. And the reason for that is neither 8 nor 12 is divisible by 5. And because neither one of those numbers is divisible by 5, you can't divide them into 5 identical arrangements. So digging in a little bit further, with 8 balloons, 8 blue balloons and 12 green balloons, the greatest number of identical arrangements that Lucy can make is, well, it's going to be 4, because that's the largest number that divides. Oops, that's a 5, not a 4. That's the largest number that is going to divide into both 8 and 12. And we call that a greatest common factor. Greatest common factor is, of course, going to be a vocab word, and I suspect they're going to give us another shot at defining it here soon. So the textbook wants to know, how could we use a greatest common factor to determine the greatest number of arrangements that Lucy can make if she has 10 blue and 15 green balloons? Well, we just have to find the largest number that will divide into both 10 and 15. And now that we're done playing with balloons, it's in time to truly define these things. A greatest common factor is a factor of 2 or more numbers. Sorry, not greatest, I should say common factor is a factor of 2 or 4 more numbers. Meanwhile, the greatest common factors of 2 or more numbers is the greatest common factor of 2 or 4 numbers. Yeah, that's really smart. Let's use the terms in the definition. The greatest of the common factors of 2 or more numbers is the greatest common factor. The greatest common factor is abbreviated with GCF. That's a term you guys should know by now. You should have used it throughout elementary school and 6th grade. You can find the greatest common factor of 2 or more numbers using a variety of different methods. Some of these methods would include listing the factors, boring, or making a factor tree. Somewhat boring. I prefer upside down division, and I will show you that. But first, let's see what the textbook has to say on the matter.
The greatest of the common factors of 2 or more numbers is called the greatest common factor, or GCF. One method for finding the GCF of 9, 15, and 18 is to use their common factors. List the factors of 9, 15, and 18. The common factors of all 3 numbers are 1 and 3. Since 3 is...
Now let me talk for just a minute about what they did there. And the factors of 9, you should have done this in elementary school, were 1 times 9 is 9, and 3 times 3 is 9. 15 is 1 times 15, and 3 times 5. And 18 is 1 times 18, 2 times 9, and 3 times 6. Does that ring a bell from elementary school? Let's keep going.
Greater than 1, the greatest common factor is 3.
Okay, so you can see there the factors that they listed. The biggest one that all 3 of those numbers have in common is 3, and that makes 3 the greatest common factor. Making a list like that for little numbers like 9, 15, and 18, I think, or something along those lines, that's not too hard to do. But what if I gave you 5,280 and 4,745, and I told you to find the greatest common factor between those 2 numbers? It'd be kind of hard to do it using the method we just saw. That's why we need to use other cool things like factor trees. And as awesome as factor trees are, that's not what we're starting with. Instead, the textbook wants us to start by listing the factors to find the greatest common factor of both 12 and 28. And then what does it mean for a number to be a factor of another number? That means it is something that you can multiply by to get to the other number. So let's take a look at some of these here. Well, this is a cool way to do it. We're going to select the squares to list the factors of 12 and 18. 12 is going to be blue, 18 is going to be green. So 12 is first off 1 times 12. 12 is also 2 times 6. 12 was also 3 times 4. And then when we went to 28, 28 is 1 times 28. It's 2 times 14. It's 3. No, it's not, but it is 4 times 7, and that's all the factors of 28. From here we can take and see what's the biggest one that they share. It's going to be 4. Therefore, 4 is going to end up being our greatest common factor. And you can see this right here, where they say drag the values to indicate the common factors of 12 and 28. Well, we've got the chart here, right, that is what we made just a minute ago. There's your factors of 12. Here's your factors of 28. And we want to know what are the ones, the greatest ones that they have in common. Let's take a look at that. What are the ones they have in common? They have a 1 in common. They also both have a 2 in common. And they both have a 4 in common. So 1, 2, and 4 are going to be the common factors. Of those common factors, 1, 2, and 4, which one is going to be the greatest? Well, that's going to be 4, just like we talked about just a little bit ago. The answer checks, easy math. Anybody can do this stuff, if the numbers are small like that. Now here's a good question. Can the greatest common factor of two numbers ever be 1? If so, give an example. Well, the answer is yes. Think about 1 and 3. I'm sorry, not 1 and 3, 3 and 5. What's the largest number that will divide into both 3 and 5? It's 1. 1's the only number that will divide into both 3 and 5. Therefore, 1 is going to be the greatest common factor. We also refer to that as being relatively prime when the only common factor between two numbers is 1. Now it's going to be your turn. Use a list of factors to find the greatest common factor of 8 and 32. Go ahead, pause the video, do this on your own. Did you get it done? Let's see what I end up doing here. I'm going to start off, with 8. So 8's factors are going to be 1 times 8, 2 times 4, and that's really all my options for 8. 32 is going to be a little bit more exciting. 32 is going to be 1 times 32. It's going to be 2 times 16. 3, nope, but it will be 4. 4 times 8, and that is all the multiples of 32. So we can take and see first, what do they have in common? Well, they share a 1, they share a 2, they share a 4, and they share an 8. And which of those is going to be the greatest common factor? Well, the answer is, of course, going to be 8. So now we can go back to our problem, type in 8 right here, and hit the check answer. Answer checks, everything works. Easy math. Now I think that's going to be a really good spot to stop part 1 of this video. Looks like we're probably going to have 3 videos here the way it's tracking right now. So we're going to end part 1 here, and we will come back and work on part 2, where we start learning how to do this using big kid math. You know the kind of math I'm going to require of you in your homework, not what we just did. What we just did, that's little kid math. You're big kids now. See you in the next video.